Okay, and we are back. Pardon the delay. I think there's been a couple days before I could get back in here to record the next set of lectures here. But it is good news because you guys have been with me as I finally got my first haircut after all the corona nonsense. So here we go. All right, that's what you guys came here for. Anyway, we were making our way through the electrophilic aromatic substitution portion of chapter 18. And remember, we had gotten to the important idea of the mechanism that's at place, which is to generate an electrophile, the ring attacks, and then we finish by reforming the aromatic ring. So we're going to just continue on with that. We just have a couple of quick things to talk about. And the first thing is, or I should back up here for just a second. Remember last time we talked about the halogenation. We can add chlorine and bromine pretty easily to an aromatic ring now. We just have to go through and follow our mechanism, right? So I can just kind of scroll up there so you guys can see. Br2 or Cl2, some kind of aluminum or iron complex. We can generate a electrophile. Essentially, it's a Br+, although we have to be careful. We don't really want to draw it that way. Some books do, some don't. You know, there's different variations with this. It's not really all that important, aside from the idea of that by binding the bromine to the aluminum, we end up weakening the bromine-bromine bond, which makes it easier to attack, and then all this stuff can happen, right? The ring attacks, we end up generating, we end up putting the bromine onto the ring, we end up generating a carbocation. That's going to be important, right? And then at the end, we come back and reform the aromatic ring. We just talked about the two different ways that you can draw the arrows for that, okay? Perfect. So, and there's that, right? So we could go through and I could erase every instance of bromine on here and replace it with chlorine, and we get to the exact same point, okay? So all we're going to do now is just kind of continue on with some of the other examples that they have in the book here, right? And the next one they talk about is something called sulfonation. Now, sulfonation is interesting, okay? Let me write that a little bit bigger. I had some comments that it was hard to see. Oh my gosh, I can't. Sulphonation, my goodness. Can't talk and write at the same time this morning. So I had some comments that it was kind of difficult to read the notes. I hope that, again, if you guys are having problems with this, just please let me know and I'll see what I can do to adjust and take care of some stuff for you guys with that, okay? I know this format isn't exactly what I would prefer to be able to. I'd love to have you guys in the classroom here so we could talk about it, but the rules are the rules, right? So here we are. Anyway, sulfonation. So here's what sulfonation is. We take our good old buddy, Mr. Benzene, and we add in something called fuming, okay? Fuming sulfuric acid. Now, if you guys have been paying attention all along, which I know you guys have, how many instances have we seen sulfuric acid used in organic chemistry? And the right answer is everywhere, okay? Sulfuric acid is just one of these. I believe the last time I looked this up, and I did actually look this up, welcome in my life, right? It's the second most common used, or one of the second most commonly produced chemicals industrially. So literally by the tanker full, right? Kind of shipped around. And it's because it's such a useful and important and versatile reagent, especially in industrial applications, right? So anyway, we see sulfuric acid a lot, and so I just gave you guys some trivia, and you're like, oh, okay, yeah, I can't wait to, write that down in the next instance of Jeopardy. But the point being is, as useful as it is industrially, from our perspective, when we have sulfuric acid, we can do a lot of chemistry with it. And that's good, and also bad, right? Because remember, one of these concepts to start keeping in mind is selectivity, okay? Sulfuric acid is not just going to react with an aromatic ring, it's also going to react with any bases that are around. If there's any amines, right, it's going to protonate those first, and then it's going to shut down all this other stuff, right, and change the chemistry and all this. So there's a lot we have to pay attention to with sulfuric acid, right? But anyway, that aside, if we start out with an aromatic ring, we add in fuming sulfuric acid, right? And at the end of the day, we end up adding this group, okay? So we end up adding an SO3H group onto there, okay? Right, so we end up adding that group. Now, what is this here? Well, this is still a pretty darn strong acid, okay? And so we add sulfuric acid, really strong acid, and we end up generating a acid at the end of this also there, okay? So, and this is going to be important because this is an acid. And the first thing you guys should always think about is if you see an acid, it's going to act like an acid, okay? So, hopefully that made sense. So let me talk a bit about this. What is fuming sulfuric acid? Another way you might see this written is like this, okay? So SO3 over H2SO4. So let's pause here for just a second. I came from, or I was born in North Carolina, and I lived close to the mountains of North Carolina for quite a while when I was growing up. And there was a mountain out there called Mount Mitchell, and Mount Mitchell is the tallest mountain east of the Mississippi River, okay? Now, man, I'm just loading you guys up with trivia today, all right? So anyway, I remember when I was young, we used to go hiking out there, and you reached a certain altitude on Mount Mitchell, and everything was just dead, okay? Right? It was really just spectacular in the sense of, whoa, how did this happen? Right, so it was a bunch of green trees, you hit a certain elevation and dead. Okay, and the reason why is because there used to be a bad acid rain problem, and that acid rain just killed everything above a certain elevation. Okay, and this is why. Okay, so not to get too far into the environmental aspect of that stuff, like I said, if I was teaching an environmental chemistry course, we could spend more time on this, right? But what happens is when you take SO3, right, sulfur trioxide, and you dissolve it into water, you will end up making H2SO4, sulfuric acid, right? So if you pause and you're like, oh, that doesn't sound, well, think about it. SO3 plus H2O makes H2SO4, right? So that's how they make sulfuric acid. They burn sulfur and they bubble that through water, right? And they make sulfuric acid. So what happens then is it reaches a saturation point, and what they do to make fuming sulfuric acid is just kind of keep pumping some SO3 in there to dissolve the SO3 into the sulfuric acid, okay? So that's why they call it fuming, because as soon as you open this up, right, the SO3 kind of fumes out of there, okay? So anyway, all we're saying is we have this dissolved in sulfuric acid, and we have equilibrium we could discuss, and solubility and all that kind of stuff, blah, 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 blah. Who cares, okay? The point being that, right, this is just a gas that's dissolved in sulfuric acid, which is essentially just an aqueous solution, right, is what it is, right? So this is where acid rain and all those kind of ideas come from. Here's going to be our nucleophile, okay? So we're back to talking about organic chemistry. There's going to be our nucleophile. SO3, right? SO3 looks like this, as if I asked you guys to pause and draw the Lewis structure. Although there are resonance forms of this, right? We have resonance forms where we can put a positive charge onto that sulfur, okay? Pretty easily. Okay? And there it is. And then we could go around and we could, play the helicopter here, right, and move the negative charge around, right, in any different way in resonance. And right, this is a classic example of resonance structures that we can draw in general chemistry. And now for you guys in organic, this should be, day one stuff, okay? But there is our positive charge on the sulfur. Good, great. Let's use that. Let's put it to use, okay? So there is our nucleophile that gets generated, okay? So we have to reach out with our ring to grab that. So let us, today's a green type of day, no, red type of day. Let's do that, okay? So SO, good. See, in red to a sulfur, boom, boom, and boom, and a positive charge there. So let me zoom in here a bit, because I know kind of squishy things there at the end. Perfect. Right, so we have an electrophile, ring attacks. Can we mix these two together? Can the ring directly attach this one here? And yeah, you can, right? And I think, so looking at, that's what the book does. Which way's right and which way's wrong? Well, obviously, since I'm doing it, I am always correct, right? That's, okay, hopefully you guys understand that I'm joking around. Either way, you would be fine, right? Either way, you guys would be fine, right? This is just a resonance form. Remember what we know about resonances and them existing and all this kind of stuff, right? Blah, blah, blah. Okay, so now we have done the attack on the electrophile with the ring. Now we have to go back and reform that. Remember, here's where a lot of points get missed. Remember, we grabbed the hydrogen that is bound to the carbon where we added our group, right? So let's do that. I'm going to copy and paste. And say duplicate, bring that down here and give myself some space to work. Okay, so some kind of base comes in. You know, what could it be? Probably some water, right? Because we are doing this in sulfuric acid, right? We do have water around. That is our solvent. Our solvent is always present in the highest concentration. So likely some water is going to be coming in, although does it always have to be water? No, right? Could it be any other kind of basic stuff? Of course, right? So there, in red we added this, okay? And then we made a nice neat bond in green. Fantastic. Now, for those of you who are paying close attention, right, say, hey, right, we've got a negative charge there. Well, think about this for a second, right? What is going on? So let's back it on up here, right? So how did we start out this reaction? Well, we started this out in sulfuric acid, right? So we're in sulfuric acid. Are we going to leave a negative charge around? Probably not, right? So at the end, we're just going to do an acid-base reaction here, right? This negative charge is going to find a positive from something, okay? So we can just leave it generic as H. Whoa. Well, let's do a little bit better than that, please. Okay, we can find an H plus from something. Is it from the initial sulfuric acid? Could be, right? Is it from the H3O plus we just generated here in green? Could be, right? But anyway, this is going to find a plus, all right? And then finally, we end up with our product. So let me do this again because the more colors I add, the longer it takes. And I don't want to spend 30 minutes changing colors for you guys, right? But that's why we came here. Okay. And in black. Perfect. Okay, so now we have this group there. First question. So what? Well, here's something useful, okay? Well, we don't really talk too much about the chemistry of sulfates and all this, but industrially, it's an important reaction because our sulfate here, right, our sulfate as opposed to our sulfurous group here, right? That's actually what's used in common, in more modern, I should say, not common, in more modern soaps. Okay, so if you take a look, right, you're in the shower and you're having your deep shower thoughts, and you look at the back, you see ammonium laureth sulfate and ammonium lauryl sulfate. Those are the two common surfactants that are found in soaps, and they're based off of these sulfate groups here, right? And from my understanding, the way that they are kind of industrially formed is through this kind of process. Now, has that changed and will that change, all this kind of stuff? Maybe, but that's not, again, that's not too important. What can we do with it? Well, and on page 796, it kind of gives us the answer, right? So on page 796, it talks about making this and then getting rid of this group, okay? Now, how do we get rid of this group? Well, it's actually pretty easy. There's two ways to do it, okay? So taking this exaggeratedly large group here, right? So SO3H, okay? If I put this into dilute, I don't know why I have trouble spelling this morning. If I put this into dilute sulfuric acid, okay, I end up getting rid of my SO3 group here, whoops, excuse me, and I end up replacing it back with a hydrogen. Okay. And remember to go this way, I put it into fuming, right? H2SO4. So we kind of end up generating this cycle. I can add my group and I can remove my group. And so we're going to come back in just a little bit and talk about why this is useful. Now, there's another way to remove this group, and that's just by heating this up, okay? So if I take this group here and I heat it up, I end up converting this back into SO3 gas and ends up kicking off all this kind of stuff, right? I believe I posted a link for you guys about that, and it kind of talks about it. Why would we care whether we heat this up or whether we put it under acidic conditions, or what's the difference, or what's the point? The point being this, right? On paper, chemistry always works for us as long as we follow the rules. In reality, when we get into the lab and we want to get rid of this SO3H group, we might have to just heat it up. It might just be easier, cleaner, whatever it might be, rather than putting it into dilute sulfuric acid, okay? So practically speaking, the more ways we have of affecting a transformation, the better it is for us. But to summarize, we can add this SO3H group and we can get rid of it, okay? We can add it and we can get rid of it. That's going to be really important. We're going to talk about blocking groups, okay? Or protecting groups might be another way, okay? Fantastic. Let's go on to nitration then. A similar setup, a similar idea, but equally as important. Nitration, we're going to be adding a nitro group. Start with Mr. Benzene, right? We drop some nitric acid into sulfuric acid, and we end up generating, or I should say we end up adding a nitro group to the ring. Fantastic. How does this work? Well, it's going to work through the same methods, right? We have to generate a good electrophile, the ring attacks, and then we have to regenerate the ring, right? We're just playing the same game here. Let's pause for just a second. What do we have? We have nitric acid, a really good acid, okay? One of our 6 strong acids. We have sulfuric acid, a really good acid. It's one of our 6 strong acids. Hopefully that comes out on the recording as annoying as it just sounds. The point being, right, we have 2 very strong acids that we mix together. And yet, something happens. Well, because remember, when we first introduced this idea of strong acids, we were kind of hand-waving some stuff, right? And really the measure of the strength of an acid is related to its pKa, right? And if you take a look at the pKa for nitric acid, I'm assuming you're all furiously Googling away at this point, right? And you look up at the pKa for sulfuric acid, you'll see they're not the same. In fact, sulfuric acid will have a lower pKa, right? Sulfuric acid has a lower pKa. What does that mean? Oh, geez. Remember, the lower the pKa, the stronger the acid. So these are both strong acids. This is stronger, right? So that means the stronger acid is going to act like an acid, okay? So this is going to donate a proton to nitric acid, and it's going to end up generating our our electrophile along the way, okay? So don't get confused by it. I know it might be very different from what we've seen before, acid plus an acid, and it still does something, but the same idea is at play. If you have a strong acid, make it act like an acid, right? Remember, how do we act like an acid? Acids will donate, right, a proton. They will end up losing a proton. So that's what we're going to do. Let's draw it out, okay? So here's our buddy. We're going to generate our electrophile first. There's our buddy nitric acid, okay? Let's bring in sulfuric acid. I might have drawn these too big. Live and learn, right? Okay. So we have to do an acid-base reaction first. Okay. So now we have a choice. Right? Now we have a choice. And the choice is, right, where is the hydrogen from sulfuric acid going to go, right? There's 3 oxygens here. Now, I know what you guys are thinking. Say, that is an easy answer, right? We've got a negatively charged oxygen, right? So I know that we're going to end up adding that there. Not quite, okay? Here's what happens. Let's do red just to kind of keep things simple. We make a bond, we break a bond. Okay. So what happens at the end of the day here? Let's continue on. So N, here, negative charge. Now we've got this here. I should be careful, we've got that there. Okay, so what do we have after this here? Well, look, what is this right here? Okay, so that is our good old buddy H2O, a very great leaving group. So let's make it leave, okay? So let's make this leave. Okay, there it goes. So what do we end up with? M double bond O, positive charge. O here, double bond with that, right? Plus H2O, right? So we end up generating some water along the way. We end up generating a NO2 plus, right? A nitronium ion is what it is. Now, what do we know about nitronium? It's a really good electrophile, right? This nitrogen in the middle, we see a positive formal charge on it. But not only that, we see a positive formal charge, but it also has double bonds coming off. That means it's pretty susceptible to be able to accept an incoming set of electrons. And that's going to be an important idea when we get to the carbonyl chapter. We're going to see a very similar setup to this. Not necessarily with a full positive charge, but we're going to see an atom that is doubly bound to a set of oxygens, and that's going to be very susceptible to to nucleophilic attack, right? So a negative charge is going to come in and hit that, okay? And that's what's going to happen here. So this is our good electrophile, right? There is our good electrophile right there. Now we have to have the ring come in and do its thing, right? So next, ring comes in. You guys can put me on double speed at this point, right? Because you already know what I'm going to say, because now it all looks the same, right? Ring comes in, it hits that nitrogen, we make a bond, we break a bond, we kick that up, right? So we end up doing this, okay? Oops, that's in purple. Nitrogen here. So we have oxygen now, and then that there. Positive charge, okay? Ring does its thing. Now we have to come back and regenerate that charge. Remember, we are doing this in nitric acid and sulfuric, so there's probably water is going to come in and do its thing, okay? So let's just do that here together. All right. Oh no, I ran out of room. Ugh. Let's make that look a little bit nicer. And then I'll zoom in here so you guys can kind of see this, hopefully. Okay, right, so attack the electrophile, break the aromaticity, reform the aromaticity, end up adding the nitro group on there. Nitro groups are extremely important groups, because they're going to be a precursor for us to generate amines on a ring, okay? It's not so easy for us to generate an amine to add directly to the ring. We can do it, right, but there's a little bit of shenanigans that we have to do along the way. But adding a nitro group, cheap, easy, effective. We usually run one of these reactions in the lab, right? It's actually one of the best labs because you come in and you get whatever aromatic group, you mix the two acids together, and then you stare at the wall for a while because it's just you just have to let it go, and then it's easy to clean up, it's easy to work with. But anyway, so a very, very common and useful route to generate an amine. Okay, I'm not saying that nitros don't have use to them, right? In fact, maybe I shouldn't talk about that one. There's uses that they talk about nitros in the book, right? I'll let you guys read about it in there. I don't know about the visuals of describing some of the maybe less benign uses for nitro groups. But anyway, there it is, right? And they talk about how to generate the amines and the nitros in here. I'm going to pause on that for just a second, and we'll come back to that a little bit later once there's another concept that I want to talk with you guys about first, okay? So on page 798, right, 798, they talk about how to reduce these into the amines. I'm going to bring that back in one of these later lectures, okay? Cool. All right, what else? Okay, so that's kind of the next major point or stopping point for this, right? So now we can add halogens, chlorine and bromine. We can add sulfate groups, right, the SO3s, and we can get rid of them. That's going to be important. And we can add nitros, and nitros are going to lead into amines. And we'll come back to that in just a minute, right? So we have a pretty diverse set of things that we can add to a ring, except we're missing one important group, right? We haven't talked about how we can add a carbon group directly to the ring, and that's going to be the next lecture, okay? So that's it for this chunk right here. I think we've spent enough time on this. Hopefully at this point this mechanism is sinking in. The mechanism's not going to change when we get to the next part. We're still going to generate electrophiles, still going to have the ring attack, it's still got to regenerate the ring, okay? So I will see you guys in just a bit for the next video.